Okay, I am starting up the stream. Looks like it's running. Hi everyone, this is TigerHawk3, and today I'm going to, I think, finish showing the Python deck. I've already written it, but I kind of wrote it offline because I felt like it, and now I'm gonna just show you what my changes were. Kind of a bunch of stuff. It's all in the GitHub commits. You can check it out if you want, but here we go. I'm going to be referring to a diff so I can see what I changed. All right. So first, we have this. We do have an import at the top now, and that's for multiprocessing, which is going to allow matrix multiplication to be up to n times faster, and being the number of processors your computer has, which might also be the number of cores, whatever. So if you have a quad-core machine like I do, it will be up to 4 times faster. Not necessarily 4 times, might be like twice, 2.5, somewhere around there. There's overhead. But in theory, right? Multiprocessing, and again, I am doing this with one monitor instead of my usual 2, and this is my first Python stream where I only have one monitor. So I've got Notepad++ and OBS and Chrome and the diff, and everything's kind of squished, so it's a little weird, but we'll see. We'll see how this works. So that's what I've got first. Next, here's a couple things. This is the concatenation thing. I think I added... Did I add concatenation? I don't know if I did on the last stream. I don't think I did. So concatenation is no longer done with the plus sign or plus equals. Now, as you can see, I have a bunch of aliases that point to self.call, which is invoked when you call an instance like it's a function. So you can use just the call syntax, which is shorter and easier, or if you feel like it, you can do these. You could have bound these afterward anyway, doesn't matter, but you know. Note that this is different from the standard library implementation of collections.deque, which uses plus for concatenation, and this uses call syntax for concatenation. And I have this new member variable, or instance attribute, whatever you want to call it, invoke MP. This is the size at which you want to invoke multiprocessing for matrix multiplication. And that is the largest dimension of either matrix, I believe. Largest or smallest? I think it's largest, but we'll see later. What else? Okay. And then we wait a whole bunch. Here we go. This is the next thing that we've got. So let me show you. Here's what happens when... how about a different window? This window, great. And let's see if this works. We got it? We got it. Awesome. So, L equals list. Great. L dot append 0. Great. L dot append L. Yes, we can do that. What do you think will happen when we show L? Because L will show 0, and then a representation of L. And that L has to show 0 and then representation of L, and so on and so forth to infinity. But no, it doesn't. You get a little representation that shows it's the same list, which is just ... meaning this is it's self-referential. So mine didn't do that. So we have to check, instead of just joining all the items in there, we're gonna say it's going to be this specific thing if the item that we're looking at has the same identity as the item itself. Otherwise, it is just get the repro of the item going through self, that sort of thing. Notice this is a 106 column line. The standard is 80, and that 80 character line comes from ye olde terminals, where you had 24 lines, and each one was 80 characters long, and that's what you had. That was the hardware. So if your lines weren't 80 characters, it wouldn't work. Nowadays, we can have anything we want, and of course, if you have a line that's like several hundred characters long and is this big, it kind of gets hard to, you know, physically read and tell what's going on. So it doesn't mean we have an unlimited line length and we can like scroll as much as we want. You could have a line that's like 20 million characters long. But I think 100, 120 is generally good. That's what I like. As long as it feels right and isn't too crazy. But limiting it to 80 at all times, no matter what, is not great advice these days. So I actually don't know how this handles cross references. What if you have L that contains another list X, and X contains L? I actually don't know what happens. I wonder if it breaks. L is a list, X is another list, L dot append X, and X dot append L. I've never tried this before. I wonder what happens. Aha. X probably the same thing. I don't know how my code would handle that. It would have L, which contains X, which contains L. I don't think mine would handle this properly. Maybe another stream to figure out how to do that. Because each repro would call the repro method. Turn that off. So we would have a deck, and inside that deck we would have, let's say, a deck A and B, and A would have a reference to B, and B is not the same as A, and within B we would have A not being the same as B. Yeah, I think that wouldn't work. So not sure how that would be handled, but maybe we can figure it out later. But this at least avoids the problem of having an object that contains a reference to itself, if not a circular one. What is that called? Recursion and dependent recursion? Something? I don't know. Anyway, where are we? What's next? Okay. At bool, we start having stuff with add and call, etc. Okay. Okay. I've changed add to to call. And then we have some nice little examples here of how to use this weird thing. We have a few decks here, ABC, and if you have this expression with first construct an empty deck, and then call it, and then pass A, B, and C as arguments, you will have a new deck that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, so it just concatenates those all together. Same thing for this. You can call something and pass it one argument, and then call that, pass another one. In chat, Behi667 says, hey, good morning. Hello. So you can do that. If you take a deck that already exists, has a saved reference, and then call that, concatenate, then you are modifying A. So the reason we have a new empty deck here is so that we're not mutating any deck that we already have. And this says we're going to get B, and we're going to concatenate C onto that. So C is just like what it was, and B is now 4, 5, 6, 7, 8, 9. And then we take A, and we add 4, 5, 6, 7, 8, 9 to it. So A has 1, 2, 3, 4, 5, 6, 7, 8, 9, and B just has 4 through 9, and C is unchanged. So that's what that is. I notice I don't have a blank line between a lot of these. Maybe I didn't care. But usually I do that. I don't know why that's not a thing here. Maybe something happened with... I don't know. Anyway. So here's call instead of add, because add does something different now. Okay. Here's a large difference right here. Matmul. Matrix multiplication, which is invoked with the at operator, the at sign. At. Because it's matrix multiplication, you get it? Matrix, it's so funny. The PEP for this, basically explaining why they were going to have a new operator and magic method, was pretty entertaining. They weren't super sure what to go with, and it ended up being, you know, this is probably fine, and it's kind of funny with, you know, matrix multiply. I don't know. That's what they went with. So this is matrix multiplication, and yes, it is kind of long. Matrix multiplication is where you have basically a 2D sequence and a 2D sequence, and when you do a matrix multiplication on them, you get a new 2D sequence, and if you have A matrix multiplied by B, you start with the first row of A and the first column of B, and you multiply the first item by first item, and then second item by second item, third by third, fourth, etc., and then you get the sum of all of that, and that is the first element of the first row of your new 2D sequence. And then you go with the first row and the second column, and you find the sum of multiplying all those together, and then the third column, and then the fourth column. I don't know how much space I have. So you do this, and then that, and then that. So still going on the first row of the first one until you have all of the columns taken care of, and that's the first row of your new 2D sequence. And then you go to the second row and you use the first column and the second column and the third column, still with the second row. Find the sum of each of those products, and that's the next row, etc. That's a lot of calculations. It can take a long time. There's more than just the naive brute force method, because ordinarily, what I've implemented here, the easy way, is O of n cubed, which gets really big, really fast. I think the better ones are like O of n to the 2.8 or 2.7-ish, which doesn't sound like a lot, but it really makes a big difference in computation time. So, if you matrix multiply something that isn't a 2D sequence, like a deck or a list, I also have iMatmul, so you can have a deck matrix multiply by another deck, a deck by a list, or a list by a deck, so that's cool. Or a string by a deck, you could totally do that. If you have a vector, meaning not 2D, then it promotes it up and finds the result for that, and then goes back. So if you have something that's just like a one row for A, that would ordinarily go like, right? Something that's one row, it'll put that in another sequence. So it'll be a 2D thing that has exactly one row in it. And for B, since it needs, a column, if you have just a row vector, or I guess it'd be a column vector, but it's just like a simple flat sequence, then it makes it a 2D sequence with each element being its own little row. And then you have something that you can, go through each row. So it does all that, and then after it's done, it demotes it back. So if you have a row vector matrix multiplied by a column vector, or another row vector, something or other, if you just have like a deck of integers matrix multiply by a string, you get the first number multiplied by the first string, or the first character, second number multiplied by the second character, etc. And then you add all those together, which is concatenation, and then you get that result, which is similar to finding the sum of just vector multiplication. So that ends up being what that is. Vector matrix, 2D matrix, etc. Hakan in chat says, morning, bro. Hello. So, N1, what is this? Oh, this is a dimension. So first we have to find the width of this one, which is A, this matrix itself. So we have A and B, and we need to find the width of A, because that's what we're going to be going along, right? So we need to find that length, and if it's not a thing that we can do, because let's say len of self is, if it's just a deck of integers, just a flat structure, then self 0 would be a number, and len of a number is not a thing, you get a type error. So if that happens, then we say, just for now, in this method, then we're going to create a new one, and it's going to put itself inside a list. And now it's 2D. Great, that's the promotion. And then we try to find N1 again, and we say we have coerced self. And if we didn't have to do that, we say we didn't have to do that. M is the height of this matrix itself, and N2 is the length of the other one, which is how many rows it has, basically. If n1 is not equal to n2, when you have two matrices and you're multiplying them of A matrix multiplied by B, you have something of n length, sorry, m by n, and it must be n by p. So the point at which they're, going this way and that way has to be the same length. And so if they are not, then we say width of left operand must match height of right operand, and we report what they are. And then we find the width of the second one. If it doesn't have one, then because it's like a row or column vector, then we take each element and put it into a list, and then we kind of make it 2D, and each one is its own little row. We find that, etc. We say we've coerced the other one. If we didn't have to do that, it's false. And then we have... Why do I have this in there still? Didn't I just do that? And 1 being len of self 0. Len of other. I don't know why I have m that I've already done, which is len of self, which hasn't changed since then. And n1 being len of self 0, which it already is. N2 hasn't changed either. I think P was the only thing I had to work with. I don't know. I think I could have taken all that out, but it's okay at this point. I'm not going to have another commit just for that. I will write it down though. Should be just... because I already had most of those things. Okay. What else have we got? N equals n1. N1 is one of the dimensions that has to be the same, and that is going to be basically the shared dimension. Now I find which is the largest dimension between m, n, and p. And this is what I'm checking against the invoke MP attribute. So if the largest dimension out of either matrix meets some threshold, then we will, or does not meet some threshold, then we're just going to calculate it in a single process, because it's actually faster. For my machine, doing matrices of small integers, it's faster to do it in a single process. For square matrices, I should say, of smaller than 150, it's faster to do it in one process. So I have a 150 by 150 matrix of small integers, doing a matrix multiply on another 150 by 150 matrix of more small integers, and if the dimension of those matrices is smaller than 150, then this is actually faster than multiprocessing. Not sure why there's so much overhead, but that's okay. And if it meets the threshold, that's what this else is going to do, we're going to save the other one as an instance attribute for this, for a little bit, which is going to matter. And then we find the size, which is just how many cores you have, the CPU count. And then we're going to make a multiprocessing pool. And we're going to use that multiprocessing pool IMAP method, which is an iterator map. Works kind of like the built-in function map, only it's multiprocessing. So you need to pass it the function that you're mapping on, the iterable that you're operating on, and the size. Now the size is it's the size of the chunk, basically. I wish you could just say split it in 4. That's what we're doing here. So if we have, say, 200 rows or columns or whatever you want, then it would be 200 divided by 4 is how many cores my computer has. And so we'd have 200 divided by 4, and that would be a size of 50. So it's going to do 50 rows per process. It's just how it works. And so this find row is something I have here, and that returns the result for one row. And since I need the other, and I have to have it in another function, then that's why I save self.other. It's actually not too complicated, the basic idea. What do we have? So we have a deck containing multiple decks, and each one is the sum of A times B for each A and B in zip row and column. So we get the row and we get the column, and we go through the first of each, then the second and third, multiply all those and find the sum, and that's going through every column in a transposition of the other, because we don't want every row. We want the first of the first column and then the second of the first column, because we actually have the column is not a structure, really. So that's why we do a transpose. The zip star iterable is a transpose. Very handy. Because we're going through each row in ourself, because we're doing this, right? And for each row, we're going to do a whole bunch of these things for each column. And yeah, that's matrix multiplication in a nutshell. And this one is also very similar, except we have, instead of a comprehension, we have a map thing. So this could have been in a function, basically, which is exactly what we do. We have this, and then it returns, one of those, and we have that for each row. Fantastic. And then, I don't know why, we delete the self.other that we don't need anymore. Probably not doing any harm, but I thought it'd be best to just tidy up that reference. Actually, maybe you're deleting it somewhere else as well, and you want to release that memory or something, and make sure there's no reference so it can be garbage collected. So here's where we demote after promotion. If we've coerced both of them, then we have just a... If we've coerced the self but not the other one, then we want the first element of the result. If we have not coerced the self, but we have coerced the other one, then we want the first element of each column, because we have like a column thing with a bunch of singleton lists or decks or whatever. So we want just, instead of a list of this thing and a list of that thing and a list of that, we just want the first element from each one. If we've coerced both, then this is a scalar, meaning a single value. Not a 2D or a 1D anything, it's just like a number. Like if you had matrices of, or if you had one vector matrix multiplied by another vector, you would just get a number, an integer, or whatever, if you had integers. Because remember, it's just, at this point, it's the sum of the product of corresponding elements. That's it. And if we didn't coerce anything, then it's already done and we can return that. Beautiful. Okay. What's next? What's next? Mul, I believe I modified. Yeah. Mul means if instead of a deck multiplied by a list, we have a list multiplied by a deck. And then it would say the list doesn't have matrix multiplication defined for it. Let's check the other one, and it does, and we'll call mul. And here we are manually invoking matrix multiplication for instead of self and other, we have to switch them around because we want to be sure that we don't switch A and B because it's not commutative. A matrix multiplied by B might not have the same result as B matrix multiplied by A. So we do switch them around. This is where we have something at equals. It's pretty common to have objects and references in this situation stay the same and just be mutated. But since you could have a vector matrix multiplied by another vector and just get a number, you can't really do that. So it just says make a new one and then assign it to this. Syntactic sugar for that, which is what it is. The old reference for this deck is discarded without any attempt to modify this deck in place, as the result might have different dimensions, shape, or even type. That's right, it could be a deck turning into a string because of promotion. Add is now element-wise. If we have a deck with A and B, and we add that to something with C, D, and E, then we would get A plus C, B plus D, and since it just uses zip, the longer one is discarded. Same thing for radd. Instead of self and other, we have other and self. Because what if it's types where plus is not commutative? Just in case. iadd does the same thing. We go through this deck itself and the other iterable, whatever it is, and then we just update the element. Sub, same thing. These are all going to be very, very similar, except here we have plus, and here we have minus, and minus, and minus. Mul is different, because we want to be able to multiply a deck by an integer, and get that deck, repeated so many times. So other can be an int or an iterable, which is a number of times to repeat this deck, or an iterable for element-wise. I think we had a lot of this before. If it's an int, and less than 1, etc., blah, blah, blah. I think we had a lot of that before, and it, still works. If it's not an integer, then we're going to try doing this. And if we get a type error on that, then we will we raise a different type error with can't multiply sequence by non-int or iterable of type whatever it is. Mul, same thing with times equal. If it's an int, something other, I don't know if oh, mul. Yeah. So this just does if you have an integer times a number. do that. Otherwise, we have other and self. Don't want to switch them around just in case. Same error message. IMUL for times equal. Does pretty much the same thing. Probably less than 1. Okay. That was similar. This is just replacing each element, multiplying, etc. Just modifying in place. Okay. Now we're back at very simple stuff. TrueDiv is a single slash, switch them around, in place. FloorDiv is 2 slashes, integer division. Mod is modulus, the percent operator. DivMod with the DivMod function, equivalent to this, is all very consistent. POW with the times operator, star, etc. and so forth. Left shift, right shift, which is left shift. And this is a bit operation. Bitwise, right shift, and bitwise and bitwise XOR, exclusive OR is this. Bitwise OR. And then we get back to these, and we have less than we already had. Let's see what else we've got. I think we're almost done. Or, IOR, yes, we already had those. Oh, at the end, we need node to not have recursion. So this used to be just return a string of the element. What if it was itself? I don't think that's very likely, but it could be. So if it is, we just say node with ... If self is self.element, otherwise we can find the string of that. And the repro is just node. I'm using kind of string formatting here to do a bunch of code in a string. You can totally do that. Checking if self and the element are the same thing. Prior, next, ... Similar. But yeah, just making sure that it doesn't recur infinitely. Okay. Where are we? What's going on? 38 minutes. So, I don't yet know how to handle circular references between two decks. So I'll think of something for that. And that this thing. I don't think we need these. M is this. Did self change? No. And 1 is len of self 0. Self hasn't changed by this point. Other... Oh, other might be different. Okay. Acceptable. I'll leave that where it is. Just as a summary sort of thing. That's fine. So I just want to figure out how to avoid infinite recursion with circular references. Don't know how to do that yet, but that sounds interesting. So that's the deck. I mean, I just said a thing that it could do that I don't know how to do, so I guess it's not complete. But prior to tonight, I thought it was. And it's pretty good. It has a lot of stuff. Some stuff that collections.deque doesn't have. Like replace and remove with more arguments and stuff. And vector operations, matrix multiplication. That said, if you want to do any of those things, don't use this module, like in general. If you have simple things to do with the Deque, use collections.deque. It's going to be much faster, unless your use case is really weird and you're just reversing it over and over and over again. Because this one has O of 1 reversal. I'm so proud of that. Basically, everything else in collections.deque is faster because it's written in C. Highly optimized. And yeah, it's going to be better than this, and probably more reliable. I think I've done reasonable testing on this, but there's going to be some stuff that probably doesn't work right. I don't know. So collections.deque is going to be faster if you have lots of matrix multiplication or vector operations to do. Use like pandas or numpy, some library that has C functions written that do all this much faster and much more optimized too, not just because it's in C. Good C. What have we got? String and repro. I want the other one. Yeah, this repro I have being the same as string, because sure. So yeah, I'm not sure how to check if this Deque itself is contained in something else that is eventually printing right back to it. So maybe we'll leave it at that, or if I think of something cool, then maybe we'll fix it. I don't know. Anyway, that's the stream for tonight. It was really weird doing it with only one monitor. But, hopefully some people had some fun. Wasn't a lot in chat other than good morning, but that's fine. So, thanks for watching, and I'll see you next time. Have a good one.